Time now to check in again with our Farming Smarter team, and Farming Smarter's own Baarda is our next speaker, and he's going to be talking about sensing soil moisture. And of course, soil moisture is a bit of a rare commodity over the last year or so, especially in this region. Lewis is the on-farm research authority at Farming Smarter. He's able to use his master's degree in geography and his experience with spatial analysis and multivariate statistics to conduct field-scale research on farms. So not only just the smaller machines, but putting it onto a field scale. He came to Farming Smarter with a full toolbox of data collection, stats analysis, and capable of managing large and complex data sets. And that's really come in useful in his work. And he loves to pull stories and information from that for your use on the farm. So he's going to talk about some current research focused on monitoring soil moisture and improving irrigation management. So let's welcome Lewis.
Everybody. So that was an introduction that saves me from taking care of that. So today I want to talk a little bit about some research we've done over the last couple of years looking at monitoring soil moisture in the field. So if you have been attending our event or been connected to Farming Smarter over the last number of years, you'll be familiar with this orange instrument on the slide in the background there, and that's called an EM38. And what that is, it's a soil conductivity sensor. So we've done a fair bit of work with it in the past, and based on some of that work, we thought, we'd like to test maybe a new application for it. So as a bit of a summary of the instrument, what it does, the EM38 generates an electromagnetic field. So it creates this EM field, and as you pull it, you'd pull it in a sled, maybe behind a quad or a tractor, and as you pull it across the surface of the soil, it measures variability in that EM field. And that tends to be related to a variety of different factors. So there's a number of different parameters that we can detect with the EM38. It tends to be a really useful tool for evaluating soil moisture and soil texture. But there's a lot of literature that does shed light onto other soil parameters that we may be able to sort of dig into. Things like salinity, depth of clay pan, water holding capacity, etc. So there's a variety of things that might connect to. Our research project examined this in pretty good detail. So this is a slide I pirated from a previous presentation we did 6 or 7 years ago. And really what we found, a couple of points that are pretty important. One, those EC readings, the conductivity readings that we mapped in fields, were highly consistent over time. So we would map a field. We worked in 12 different fields for that particular project. We would map it in the spring. We would map it again in the fall. And those EC readings were highly consistent. So there wasn't much change from spring to fall as far as soil EC. And the second thing that sort of leads into this current project was EC we found to be a pretty good indicator of presence of clay and presence of soil moisture. So, wherever there's clays, it tends to hold on to water a little more tightly. It tends to hold all those ions in solution, and you get a higher EC reading. So we found that we did a pretty effective job for that. So I think correlations were sort of on that 40, 50, 60% correlated with soil moisture and clay. But some of these other parameters, we didn't see the high correlations that maybe we have seen in some of the academic literature. So because of that, we thought, okay, maybe we can deploy this to take advantage of this capacity to measure where soil moisture is in a field. To sort of step back to that previous study, we used 2 different instruments for that project. We used the EM38. In this picture, it's being pulled in that sled behind the tractor. Because it uses an EM field, it's a non-contact sensor. It doesn't damage the crop, doesn't disturb the soil. So that gives us a little bit more flexibility in its use, whereas some of the other soil conductivity instruments out there have to maintain contact with the soil, and they emit an electrical signal directly into the soil and measure how much that dissipates before it reaches sort of a paired disc. So the fact that the EM38 doesn't contact the soil meant that we could possibly deploy it in season. We didn't have to do it before seeding or after harvest. And because it relates to moisture, we thought, well, maybe we could use this to do a better job of monitoring or managing our soil moisture in fields throughout the season. So existing techniques for this, they have limitations. Hand moisture tests or soil probes actually do a pretty good job of measuring what our soil moisture is at particular locations, but we're missing out on that, filling in the gap on a full field. So, how many samples do you need to take? How many probes do you need to install to get a really good picture of how the water is distributed across the field and how that might change over time? And we thought we've got this EM38 that perhaps, we could attach it to a sprayer and collect data in season. So it gives us another month worth of information rather than a static survey sort of at time of seeding. So our questions, the opportunity here, kind of like I said, it's a non-invasive sensor. We can collect data rather easily. We believe we can integrate that with current operations, pull a sled with a sprayer or maybe suspend it from a sprayer. So if we're doing it anyways, can we do a better job with it? And the challenge we posed for ourselves was first, we have to be able to detect subtle variations in soil moisture. So if you think about highly consistent maps from spring to fall, there's going to be subtle changes between spring and fall as the soil moisture profile changes in that field. So one, can we detect those subtle changes? And then we challenged ourselves to be able to use that information in a practical way. So could we manage irrigation better or perhaps even fertilizer better with that information? This is just a quick slide that shows exactly how that EM38 measures soil moisture. So that chart on the left, that just shows when it emits that signal, that EM signal into the soil, where the bulk of the reading comes from. And the solid line, you can see that most of the reading comes from that top 60 centimeters. So that's kind of right in that root zone. And looking at some of our more common crops, 50% of the root matter is usually in that top 20 centimeters. In general, this is for a variety of crops, and 95% of root matter is in that top 90 centimeters. So right where that EM38 is actually collecting information is exactly right where the bulk of our root matter is. So it makes a lot of sense to be using this in an agricultural context. So the project itself, what we did, we worked in 2 separate fields. Each of them we mapped 3 times. We mapped once time of seeding, so right the day before, day after, right when we were seeding. The second mapping was 2 weeks after, and then 4 weeks after the time of seeding. And we did have opportunities to actually get out there and map it later than that, which I'll get into a little bit later. But it's a little bit tricky as a crop grows to really do a good job in a standing crop that's undergone quite a bit of vegetative growth. This field here was a seed alfalfa field, so because we had the bays that remained there for access for pollinators, we could actually get in between the alfalfa, so that worked out quite nicely. And then we collect soil samples as well, so we collected 15 to 20 samples from the same locations every time we did it. So we used that to compare, what's our EC, how does that compare to our moisture, and went from there. So here's what it looks like time of seeding. This is an alfalfa crop that's been sprayed out. This is actually on an unrelated project, but the picture was better than anything else I had. So time of seeding, this is what it looks like. We've got a video here. So this is what it looks like, sort of a real life application. So the crop's at a stage where you conceivably might be running a sprayer through the field. So if this wasn't a quad, perhaps we could be using a sprayer or some other equipment to kind of gather that data while we're doing something else. And then this, one of the fields we worked with, we actually partnered with the Farm Stewardship Center connected to the college. And unfortunately, out of some of the restructuring that happened in sort of the ag research world, we had to find a different location for our second year. But the nice thing about working with those, the Farm Stewardship Center, is they've got a piece of land. It's not a commercial, doesn't have commercial applications. So it allows us to take some risks that we probably couldn't take in a commercial field. And in this case, the risk we took was mapping it. We've got a pea stand here that's about, days away from flowering. And, looking at the damage to that pea crop, it's something you wouldn't do in a real life context, but we were able to give it a try. And spoiler alert, it didn't work at all. So you think about the profile of that EM38, where it collects information from. If you've got a pea plant that's holding that sled 4 inches, 6 inches above the ground, some of that key place where you should be collecting information is actually just airspace between the sled and the soil. So that made readings hard to get. The other side of it was keeping that thing level. We found that if we, it's kind of like driving over a washboard. If you hit that perfect speed, you can go nice and smoothly over it. But as soon as something goes wrong, you're bouncing all over the place. So that sled, I'm not a pilot, there's probably better terms, but left and right and forward and back. So every time it moves and shifts, you're collecting a different proportion of information from air and from soil. So anyways, long story short, not reasonable to be mapping a field that late in the season when the crop has been growing so much. So now to kind of get into the results, I think the best way for me to share what we found is to look at it in the context of the different years we worked in. So we ran this trial in 2019, 2020, and 2021. 2019 and 2021 were very dry years, whereas 2020 was sort of a typical precipitation year. And we saw differences in performance, differences in outcomes that were tied to how wet or how dry it was. So our 2020 season was actually a quite typical precipitation between April and end of August. So this chart here, I realize you probably can't see it as well as I hope, but the big red bars, that's where we did our mapping, and then the dotted red line, that's sort of our cumulative precipitation. So you can see that when we mapped it, we're right along seasonal normals, which is the green line that I'm assuming you can't see, but right around seasonal normal precipitation. So we're entering in fields that weren't starved for moisture. So here's a map from one of those fields. This is time of seeding. The way I've laid out, so I've got raw data here, but I'm displaying it using standard deviations, which means that anything that's a bright red or a dark green is actually quite an extreme value. And visually, most of that map, so red would be low EC, drier areas. Green would be high EC, wetter areas. So in my head, I think, if it's green, there's lush growth. That's how I kind of keep things straight. So hopefully that works for you. But very few areas on the extremes. And then our soil moisture is the blue circles. And in this case, I've amplified the variability there. There actually wasn't a lot of difference across the field in actual soil moisture. But if we move to June 16th, so there's a couple of things here. You see the right-hand side of that field, and this is why I kind of showed the raw data, because that right-hand side, there's obviously some error in how we've collected things. So what I think happened, what I'm fairly certain happened, is we mapped half the field, we stopped for lunch for an hour and a half, it's June, the sun came out, we went back out again, and things changed, and we didn't get, sort of those accurate results. You can actually see every other pass is quite red, and that's something that can happen just because of the sun shining on the instrument. So if it's shaded one direction and sun shining on another, you get quite a bit difference in temperature. So just one of those little, I guess, interesting things in research where things don't go right, but you kind of learn something anyways. But the analysis anyways did focus on that left-hand side of the field. So I mentioned before that in order to detect subtle variations in soil moisture using this instrument, you think about how consistent the readings are from spring to fall. Like we know that they don't change much. So if we want to detect subtle variation, we sort of have to start with a base profile. So we map it once and we say, this is what we know about the field. This is the variability, the distribution of conductivity in the field. If we want to know how moisture is moving or changing, we have to detect variations from that pattern. And that's what this is. This is a histogram of our data points. So on the top, that's basically our base profile. This is the distribution of values in the field. It's a bell curve, maybe skewed a little bit to the left, but kind of what we'd expect to see, not a lot of values on the extremes. After 2 weeks, again, this is our wet year, not a lot of change. After 4 weeks, we're seeing a little bit of change, but for the most part, that pattern hasn't changed much. So what that tells me is, how the pattern of EC changes in the field from that base profile isn't very much. It's not changing much, which means it's probably really challenging to identify any change in soil moisture distribution in the field, certainly in a wet year. This next example will be a much drier year, so drought conditions. So this is from 2021 this year. Again, the red bars are when we collected data. And we had about a third of normal soil moisture, between April and end of August. And a chunk of that was actually quite late in the season, so quite dry conditions. So at the start, we kind of see the same sort of pattern, not a lot of extremes on our EC measurements in the field. But as we move into June, a month later, we're actually seeing a lot more extremes. So we're seeing some concentration of values. So we're seeing the highs and lows being accentuated under drier conditions. And going back to this base profile idea, we're seeing a little bit more change over time in how that base profile is manifest. So time of seeding, we have a certain distribution of values. 2 weeks after, we're seeing a little bit of change, but 4 weeks after, we're starting to see things a little bit more of a bimodal distribution. So we're seeing concentration on different sides of the spectrum there. But again, this general pattern is still there. So it's, the outcome of all this is even in dry conditions where we expect that pattern of moisture to change throughout the field, we're not seeing a lot on the EC side. The EC pattern isn't changing enough that we could say, hey, we know the moisture has redistributed itself in such a way. So that's the one part. And the second part of it is we've ran correlations. So we did compare to actual soil moisture, and those correlations were about what we'd expect. They were moderately strong, 30%, 40%. In good situations, maybe as much as 60%. So when you combine those things, we sort of have a 40%, 50% correlation between our data and the soil moisture, plus we're seeing very little change in the pattern of our data. That leads me to suggest that this probably is not an effective tool to better understand our soil moisture. If those patterns don't change much, we're probably just as well off using a static model, mapping it that one time before seeding and using that to sort of calibrate a model. So using that to identify, perhaps where we can place soil moisture sensors and use a model to sort of predict what happens in between those sensors. So interesting stuff, but probably not a really practical tool on the moisture front. We did add another interesting element to it. We had the idea that, we thought if we better understood how soil moisture is distributed in a field, we might be able to manage fertilizer differently. So if you were to, for example, place 60% of your fertilizer with seed and then come in a month later or 6 weeks later and say, okay, where is the field wet enough to warrant application of an additional 40% of fertilizer? So we did exactly that. We divided this site into 3 different pieces. So we had a low moisture, medium moisture, and high moisture zone, and each of them was applied with 3 treatments. 60% fertilizer at seed, 60 with 40 topped up in season, and then 100% with seed. And it's the caveat to this is it's one trial, one location, and the other piece to it is, we would have identified the same zones regardless of whether we gathered EC data from time of seeding 2 weeks after, 4 weeks after. I mean, the same zones were identified. But interesting to see, so the red is the dry, the orange is the moderate, the wet, or the green is the wet. So if we look at the red right away, all 3 of them were lower yielding. And in fact, adding, topping up to 100, whether we used UAN or 100 with seed, that extra fertilizer wasn't used in the dry portion of the field. Whereas in the wetter portions, we did see an advantage. And in fact, the wettest portion, we did see an advantage for that UAN top-up. So these results they don't support mapping a field after seeding. The same info, those maps don't change, but there's certainly opportunity to sort of manage the field differently based on the moisture distribution that we expect to happen in there. So yeah, static models is probably enough. And again, we did that in Durham this year, so the economics of that might be a little bit different than some other crops in other years. So yeah, a little bit more to be dug into there. So that's kind of the outcome for the EM38 side of the project. To sum up, mapping things in season didn't give us anything we didn't already know 90% of at time of seeding. So I wouldn't suggest there's any value to doing that in season, but those maps I do think are quite effective. And it does lead into another project that we're kind of just getting rolling on, but we'll be applying in the field this coming year. on variable rate irrigation and moisture management. So I'm just going to quick touch on that really quick. So we've got a couple of partners connected to the University of British Columbia. Ensemble Scientific, they make all sorts of sensors, actuators, stuff like that. So the idea is to place these things throughout the field, all over the field. They're going to communicate remotely with the pivots, and the pivot's going to be able to water according to how, the information we're getting real time in the field. So maybe this is sort of the next step on managing moisture. And there's a pretty comprehensive modeling and data platform that they're putting together as well. So a couple of screenshots from that. So yeah, that's the next step in sort of the moisture management thing is actually having something in the soil and having it talk to us and talk to our pivot real time throughout the season. So with that, I'd love to answer any questions anybody has. Thanks to the CAP program for supporting the EM38 project, and this irrigation project I mentioned briefly is RDAR supported.
Did you look at your soil samples that you pulled at each point and then relate that to EC information?
Yeah, we did that. So we looked at the texture and moisture of those soil samples. So I didn't put the numbers up, but so if you look at the correlation, the relationship between our EC values and our soil, it was variable, but it was sort of that moderate, 20%, 40% kind of range. So a reasonable correlation, but yeah.
Texture? Did you texture too?
We did texture, but we haven't done that correlation yet. So. But we've done it in the past. So our past project, we did basically the same thing on the moisture and texture, and we found that percent clay was quite well correlated to the EC map.
I'd be interested to see the final map on the texture versus your EC map.
Yeah, I suspect they'd be quite close. It does a really good job of mapping that. Like I said, our previous work showed that it's a really good tool to identify where those clays are located. But as far as mapping sequentially throughout the season and being able to identify concentration of moisture, it's too subtle a change to really identify with this tool.
Any other questions for Lewis about it? Okay, we've got one over here. Go ahead.
Well, when you split apply depending on the moisture content in the field, does that give you a better ROI?
Sorry, what was the?
When you split apply depending on the soil moisture, you split apply the fertilizer?
Yeah.
So did it pay for itself?
I don't know. We haven't run the economics on it, and I think, and it's always such a tough thing. It's something I always want to include in all the stuff we do, but there's so many assumptions, so many pieces in there. But like I said, that would depend on the crop. That would depend on the year. The price of fertilizer. But I mean, if you're interested, I'm happy to chat about it.
One more over here. Go ahead again.
Just to add on to that, with the split apply, did you have? I think at one point you said it wasn't an irrigated field.
That field did get irrigation, but it was a pretty small amount. So
you were able to water the fertilizer?
Yeah.
All right. Any other questions on Lewis's research? And are those projects done, or are you still ongoing on those?
So the conductivity project is done. So we'll be wrapping that up here in the next few weeks, and then the irrigation, the variable rate irrigation project I touched on, it's about timeline. We're about halfway through, but we haven't been out in the field with that technology yet. It's all kind of under development. So hopefully this spring we'll be able to install and see what we can learn on it.
Great. Okay, well, thank you very much, Lewis. Let's thank Lewis again for sharing his research work with us.